This is Algebra 2 with trig. We're working on 3A.3. So these rational functions are going to, you could consider it to be a little bit more challenging in some cases. We're again looking at P of x over Q of x. Now P of x doesn't have to be just the first degree. It could be a little bit higher degree. Like if you look down here, we have an exponent of a square. So that's really all that that's implying. The x-intercepts of the graphs are the real zeros of the numerator. Listen to that again. The x-intercepts. Think about what x-intercepts are. The x-intercepts on your graph are where the graph is going to cross where y is 0. Well, what makes a fraction 0? Fraction is 0 when the top of the fraction is 0. So that's going to be P of x. The graph of f has a vertical asymptote at each real 0 of Q of x. It's where the denominator is 0. And we call that each because we're going to work with higher degree denominators now. We might actually have 2 vertical asymptotes. Here's a set of notes that we learned about yesterday. This is formatted in a different format. You might like this format a little bit better than yesterday. What happens when the degree of the top, that's the m, is less than the degree of the bottom? When the degree of the top is less than the degree of the bottom, we have y equals 0. That looks like yesterday's examples. That would be y equals 3 over x would be an example of that. And you can make that as creative as you would like. What if the degree of the top, look at the exponent of the top, that's the m. The degree of the denominator is n. So what happens if they're the same? Then the y is going to equal m over n. It's the ratio of the leading coefficients. Oh, I'm sorry. I'm going to take that back. We're not going to use m and n. We're going to use a and b because they should be the leading coefficients. A is the leading coefficient of this polynomial, and b is the leading coefficient of the denominators. Here, we never talked about it yesterday, but what happens when m is greater than n? What happens when the numerator is larger than the degree of the denominator? Okay? The graph has a slanted horizontal asymptote. What that's going to look like, you'd have a slanted asymptote, you'd have a vertical asymptote, and your graph would look something like that. Don't worry, we're not doing this. This will be covered in a future class. So there may be one homework assignment, I think it's like number 22 or something, that has a slanted asymptote in it. You can play with it as much as you like. You can plot some points and you'll start to see kind of how it is slanting. But this is where long division comes into play. Figures out the equation of that slanted asymptote. So we're coming down here to our first example. We're going to graph this equation. Notice what's different about this equation. We have an x squared in the denominator. Okay? Our vertical asymptote let's first say horizontal. Our horizontal asymptote is determined by the degrees. That's what these notes were about. So what situation do we have? Do we have the degree of the top is smaller than the degree of the bottom? Do we have the degree of the top is equal to the degree of the bottom? It's smaller. The exponent on top would be considered a 0. So we're going to have y equals 0. And then we have our vertical asymptote, where whatever makes the denominator 0. So x squared plus 1 equals 0. When you subtract the 1 across, you get negative 1. When you take the square root of negative 1, what happens? You're going to end up getting an imaginary number. When you take the square root of negative 1, that would be plus or minus I. In other words, you don't have any. No vertical asymptote. That means every value of x can be plugged in. There is no limitation. It's all real numbers. There's no number that can't be plugged in. So we're going to start plugging in values. We have our horizontal asymptote at 0. So that's y equals 0. So you should label that on your graph. I'm going to start with 0 in the middle. That's x equals 0 in the middle. And I'm going to pick values to the left, and I'm going to pick values to the right. We're picking 0 in the middle just with the symmetry of what can happen with an equation in this format. There is no translation right and left, so we would assume that a lot of our action is occurring without any translation right and left.
So there's no translation, it's always 0?
So it's going to be 0. So we're going to work left and right. You can pick any values to the left you like and any values to the right. So negative 1, negative 2, negative 3, 1, 2, and 3. You could pick any numbers you like. So we have to do some calculations though. Negative 5 divided by 0 squared plus 1. Negative 5 divided by 0 plus 1. What's that going to be? Just negative 5. Negative 5 divided by negative 1 squared plus 1. So what's going to happen to the denominator here? That's 1, and this is 1, so that makes 2. So we're going to have negative 5 over 2. Negative 5 over 2 squared plus 1. What's going to happen when we square negative 2? Positive 4 plus 1 is 5. It's going to be negative 1. Negative 5 over negative 3 squared plus 1. That's 9. Plus 1 is 10. So negative 5 over 10. Negative 1/2. And if you notice, we're at negative 5, then we do half of that, then we do half of that, and we're doing half of that. We're getting smaller every time. So we're up here at 5. 1, 2, 3, 4, 5. At negative 1, we're at 2.5.
Wait, are you doing?
Yeah, actually, it's negative 2.5, isn't it?
Wait, I'm confused. Why are you doing positive 5? Shouldn't it be negative 5?
Oh, thank you. That's what was weird about my thing. That's a negative 5. Thank you. 1, 2, 3, 4, 5. Much better. So negative 2 and a negative 1. Negative 3 and negative 1/2. So we're approaching this asymptote.
Wait, how do you graph -5?
Negative 5 over 2. We're taking 5. We're dividing it in half.
So it's 2.5.
2.5 apiece. So that's 2.5. So at negative 1 for x, we would go down 2.5.
That makes sense.
So the values on the right, if you notice, there's going to be some symmetry here. When we work with 1, even if you work with negative 1, if you work with 1, you square it, so you're getting a positive 1, so that's still negative 5/2. Plug in 2, you square it, you get 4 plus 1, it's still negative 5 over 5, which is negative 1. So we're getting the same number each time. So on this case, put our arrows. There's our graph. We have none. There are no vertical asymptotes. A horizontal asymptote is at 0. What is our domain? What x values can you plug into your graph? All the numbers. There's no limitation, right? There's no except. So your domain, you can plug in any numbers you want. All real numbers. What about your range? What answers can you get? Can you get 0?
I thought it was all the numbers except for
Okay, all real numbers except 0. So does that mean you can get negative answers?
It doesn't go past
Yes.
negative.
It doesn't go lower than negative 5.
So,
It's all real numbers except.
no, it's anything. Negative 5. Suppose anything more than
anything positive.
So our range is going to be negative 5 all the way up to almost 0. So y is greater than or equal to negative 5 because it includes negative 5. It includes all the negative numbers all the way up until we get to 0. Interval notation, you would say negative 5 because that's your smaller number, comma 0. It doesn't touch 0, so we use a rounded bracket. There we are. Okay, this one is like what we've done in the past. We have a horizontal asymptote. And where's that going to be? Which situation up here in our notes are we dealing with? With this equation. So our horizontal asymptote, since the degree of the top is smaller than the degree of the bottom, we're going to be at y equals 0. And our vertical asymptote, we set the denominator equal to 0. And we get x equals negative 4. So x equals negative 4 is our vertical asymptote. But Take a step back. Sorry, I am going to change that. We don't make our table with our h values in it. So what we're going to work with is y equals negative 8 over x. So I'm going to suggest to use 0. And we're going to pick numbers that go into 8 nicely. 2, 4, and 8 would work great. You could use 6. You could use 1. It may not work perfectly with 8, but it wouldn't matter. You could do it. When you plug negative 8 in here, you get 1. Plug negative 4, you get 2. Plug 2, you get 4. And you could do the same thing on this side. Plug 2 in here, you get negative 4, negative 2, and negative 1. So if you would like to come to the origin of your asymptotes, you could plot this out. You could go 8 to the left. See if we can even fit that on our graph. 1, 2, 3, 4, 5, 6, 7, 8 does fall off our graph a little bit. 4 to the left of our asymptote and up to 2 to the left of the asymptote and up 4. And we have our first branch. From the asymptote origin, we go 2 to the right and down 4. 4 to the right and down 2. 8 to the right, down 1. And there's your graphs. So we know our vertical asymptote is at x equals negative 4. Horizontal asymptote is at 0. What's our domain? All real numbers except x equals negative 4. And the range is all real numbers except y equals 0. Great questions. All right, and here's the toughie. What do you see that's different about this one? We wouldn't consider this H's and K's. No. Here we have degrees the same for the top and the bottom. So the m is equaling the n in this case. So we use the leading coefficient for the horizontal asymptote. So what is our horizontal asymptote going to be? One over 1. Leading coefficients. So we get y equals 1. How about the vertical asymptote? So our vertical asymptote is when x squared minus 4 equals 0. We're going to add the 4 to the other side. Then we're going to take the square root of the 4. That's going to give us plus or minus 2 for our vertical asymptote. That gives us negative 2. And that gives us positive 2. Notice how we got 2 vertical asymptotes. Because we set the denominator equal to 0. The denominator was x squared minus 4. So when we added it to the other side, it was a positive. And now we can take the square root of a positive. So just as you suspect, Now we're going to pick numbers inside of each of these locations. So we have -2, we have +2 for our vertical asymptotes. In between those, we have 0. Now we need to pick a value in between 0 and -2. 1 and -1. That would be very reasonable. So with 1, we'll get 1 squared is 1 minus 9. 1 squared minus 4. That's -8 over -3. That's 8/3. That's 2 2/3. That's 2.6. 2 2/3. When you plug in 0, they would cross off and you'd be with -9 over -4. That's 2 1/4. So now we can plot these. At 0, we're up 2 1/4. At -1, we're up 2.6. So we're up a little bit higher for the ones. So that means we are going to continue to approach in this direction. So now we're going to pick values to the left of -2. So -3, -4, and -5. -3 squared is 9 minus 9. 9 minus 4. That's 0 over 5. What is 0 over 5? 4 squared is 16 minus 9. 16 minus 4. That's 7 over 12. So that's just a little bit more than a half, right? 7/12. 25 minus 9 and 25 minus 4. That's 16 over 21. That's even smaller. $11 would be a half, so this is even smaller than, or closer to 1, I guess you could say. So what we're doing is plotting our points. At -3, we're at 0. At -4, we're just about a half. And at -5, we're even closer to 1. Just plugging in our numbers. Now we're symmetrical if we say 3, 4, 5. So we can save ourselves these calculations. We would expect 0, 7/12, and 16 21sts. And it will be symmetrical on this side. So at 3, we're at 0. At 4, we're just past a half. And at 5, we're just under 1. There's our graph. Vertical asymptote is plus or minus 2. Horizontal asymptote is y equals 1. What numbers can we plug into our graph? What's our domain? Right? Anything but the asymptotes. What are the range values? This is tricky. Take a look at your graph. Take a look at your graph. What is your range values? It's not happening at 1. It's not even happening at 2. It goes all the way up to there. So we can say that it's y there's two different ways to think about this. Where is it line and where isn't it line?
It's
It is y being less than 1, but greater than or equal to that location. Where's that location? 2 1/4. So y is going to be greater than that. You would really should write this twice. This is not a great format. You should write y is greater than or equal to 2 1/4 and y is less than 1. We often call that union when you combine the two together. Now our last story problem. This is a goodie. A food manufacturer wants to find the most efficient packaging for a can of soup with a volume of 342. So we know what the volume is. Find the dimensions of the can that has this volume and uses the least amount of material. So our can is going to be a cylinder. Write an equation that gives the height of a soup can in terms of the radius. There is our volume, pi r squared, that's the area of the bottom, times the height. So this is of a cylinder. We have volume equals pi r squared h. Now we know the volume is 342. So we want this to know what h is in terms of r. So we're going to divide by pi r squared, and that's what our h is going to be. So when it's asking us to give the height or find the h, in terms of radius, we're allowed to have radius but no other variables. Pi is not a variable. Pi is an exact value. So there's our height. Write a function that gives the surface area, because we want to limit the least amount of material, so we need to know how much material we're using. So the surface area of the can in terms of only its radius. So we're going to use radius again, but we've got to get rid of everything else. So here we have S equals 2 pi r squared plus 2HR, or 2 pi RH. So we're going to plug in our equation here. So we have S equals 2 pi r squared plus 2 pi r h. 342 over pi r squared, because that is our h value. Now we can do some reducing here. We can get rid of those pi's. We can get rid of that r. And we can times this guy by 2. So we have our surface area, 2 pi r squared plus 684 over r. So that's our surface area in terms of r. Alright, so we're going to graph the function using our graphing calculator. So we'll take y equals, type in 2 pi, we have to use x because r is not an option, squared plus 684 divided by R. Alright, we don't have to worry about parentheses here because order of operations keeps it straight for us. And we can graph it. I don't see a lot happening. We want positive values. Think about what we're doing. We have R as our radius, which is our X value, and we have the surface area is our Y. So we only want positive radiuses and positive surface areas. So we're going to look at our table and see where that happens at. When the radius is 1, we're going to have a pretty big surface area. And then we can start changing our surface area when we start to come down and it reaches a small number and it starts to climb back up. So it looks like all the way to 10, this is almost at like 700, so we could even call it 800. So in Windows, we're going to go to 800 just so we can see a lot of the graph. Now you're going to see a lot more of the graph. We want to know where this low point is. We know it's around 271 or something. So we're going to do second, trace. We're going to do our minimum. We got to do our left bound. So since I know this is my minimum value, we need to be to the left of that, enter. And then move to the right of that, enter. And then it says guess, but there's only one value. You can get closer if you want, it doesn't matter. Hit enter, and it gives us that exact location. When the radius is 3.78 or 3.79, if you did some rounding, almost 3.8, we'd have a surface area of 270.73. Find the minimum value of S. So S is going to be, let's see. Yes. S is going to be 270.73 centimeters cubed. This was made when we had a radius of 3.79 centimeters. Now we got to figure out our height. 342 pi 3.79 squared. 342 divided by, let's put that in parentheses to be sure our order of operation works out just fine, 3.79. 28.72 centimeters. That's going to be a pretty narrow can.